Nice. First example. Okay, can you see the screen?
Yes.
Okay. Okay, so this was like, I'll send you this as well, but this is the code which we used. Now, the first and the easiest example on the neural networks is so-called the Xor Function Network. So this will be a neural network which will try to recreate how an Xor function works. So let me just write in a notepad. So an Xor is it's a function where you have two inputs, so true or false, 0 or 1, and you have one output which is either 0 or 1, right? So you have input A and B, and then the output. So this function is if you have false and false for B, this will give you let me think, false, right? So this will be 0. If it's 0 and 1, it will give you 1. If it's 1 and 0, it will give you 1. And if it's 1 and 1, it will give you 0. So it's a non-trivial function, let's say, right? It's very easy. But yeah, so we have this. So what it means is that we need to create a network which will have two input neurons, right? Or two input neurons, let's say, and one output value, right? And we'll teach this small, like laughably small neural network will have like input layer where it doesn't really compute anything, it just sets the values. It will have a middle layer, which will be, let's say, 3 neurons, and one output neuron, which will sum up those 3 neurons and process the data once more. So yeah, but based on that, we'll discuss all the things which we were talking about before the break. So we'll see the backpropagation in action and also discuss the layers, the neurons, and how it learns, right? Okay, so and we'll see actually what is the benefit of using neural networks, right? Because as you see, we'll talk about it later. Let's keep it a surprise. So we need to create the tensors, right, as the input and tensors as the output. So I will use a panel and I'll create 4 inputs, right? So 4 lists. Maybe let's start with a single one. So 4 lists of 2 values. This will be construct tensor, right? So I'll have 0 and 0. Then I will have 0 and 1. 1 and 0. We can actually just full screen Grasshopper. We don't need Rhino yet. And 1 and 1. Okay, so those will be the inputs. Now the outputs, on the other hand, will be 0, 1, 1, 0. Okay, now we'll think about how to simplify that dataset creation, right? Right now, I'm just gonna merge it. So we need to use the component merge just to merge this is in the same order, right? So this one will be responsible for that one, this one for this one, and so on. So we need to use the merge, just like that. And finally, we can have a component which is called construct Tensor Set, right? So we have 2 tensors. Okay, so I'll just put them here. Maybe I can just zoom in for a second. Okay, so what it means is that when I will have a neural network with 2 inputs, and I expect it to give me 0 in the output if there are 2 zeros in the input. I expect it to give me 1 if there is either neuron 1 and when the other is 0, and I expect it to give me 0 if both the neurons are 1. Okay, so how do we do that? We go to OWL accord. We'll get a primitive construct network, backprop, backpropagation. Those two components are kind of important, right? So we need to construct a network and we need to teach it, right? So we'll have it here. And let's discuss the parameters. So the layers is a list of numbers, list of integers. And in our case, well, as we go back to our list, we have 2 inputs, 1 output. So the 2 inputs are actually non-computing, right? So those are just the values, right? We put the values just as if they were an output of a network, a neuron, but there is no neuron which computes anything in the input, right? So this is just a placeholder, let's say, for the values. 1 output will be actually 1 output neuron, but it means that we have a very simple architecture of essentially 1 neuron with 2 input values, right? So we need something in between, right? So this in-between layer is called hidden layer. It's hidden because you can have direct access like to an input or output to it. So I will say that this will be just free hidden. We'll discuss how do we decide about the number of neurons in the hidden layers and about the number of layers, because we can have here like 100 neurons, why not? But it's not necessary. We'll discuss it in a second, like once we teach it. So yeah, so as you see, we have 2 inputs, 3 hidden neurons, 1 output, and this is what I want to input to the layers in the construct network. 2, 3, 1. 2, 3, 1 as a list, so multi-line data. Now the activation is the activation function. We leave it as sigmoid. You have a couple of like other, like bipolar, sigmoid, and threshold. So threshold is essentially when the input value is over some value, then it will give you 1. If it's below this value, it will give you 0. Surprisingly, this is used quite a lot right now in deep learning. Sigmoid is more popular with just classical neural networks, which is counterintuitive because they give you like a better resolution, but yeah, anyway. So we leave the sigmoid. Now the alpha value, that's slope of the activation function. Let me show what I mean. So sigmoid function is actually, there is no, there isn't, sigmoid function is not a particular function, it is a description of the function characteristic, right? So as you see, S-shaped curve, and a common example of a sigmoid function is this one, right? I think we are actually using exactly this one for calculating our activation function, but there is more, right? So you can see there are different equations to get this characteristic S-shape. Now, why are we caring about this S-shape? It's because in the backpropagation process, now for those of you who know a bit more about mathematics, unlike myself, for like if you have a function, in the backpropagation, you're actually taking the derivative of the function to figure out how to affect the weight of the connection, right? So you see that if you want to lower the value, you get the value of how much you want to lower it and in which direction to go to get the smallest value, right? So those sigmoid functions have to have derivatives, right? So actually, in some learning methods, we even use the second derivative, right? But standard in the standard backprop is just the first derivative. So this slope gives us a nice derivative. Derivative of that function is, just to show you, this is the function, right? And the derivative is like that, like a bell curve, right? So, and it's continuous. That's important that it's continuous, because optimization, I mean, there is some optimization in there. Optimization likes continuous functions, right? Because it indicates the slope and it's continuous, so there are no dramatic changes in how it's optimized. Anyway, that's activation. Alpha in this case is the parameter. So if we have a slope of this curve, this is actually this minus x power, right? So there's e, the constant e, and minus x. So this x is this alpha. What it changes is actually how fast or this curve goes up, right? So it can be either like that one, or it can be either like that one. In this case, the higher the alpha value, the shallower the slope is, right? So the smaller the value, the more steep it will be, right? So by default, it's 2. With small networks, 2 is fine. With big networks, you want to, wait, that's, I'm not making the mistake, but I think anyway, with larger networks, you want the alpha value or the slope to be shallower, because if not, then there will, we have, let's say, 100 neurons, and each one of them will change just a bit, but the alpha, the sigmoid function will introduce so much change from each of the neuron that it will be just noisy. So the sum of all the changes has to be smaller. By that, we need to reduce the slope. I think reducing is increasing the alpha value, as far as I understand. Yeah, because it's 1/1 minus e to the minus x. Anyway, we will do tests. We put the activation network to backpropagation, right? So later, we'll actually loop this part. So we'll be looping the entire network with anemone here, right? But right now, because it's such a small problem, we don't really need that many iterations. We'll just put the data set as it is, right? So we have the input and the output data set. So it's here, input and output. And it works, right? Okay, how do we know it works? Well, again, we can go back to our visualization tools. I think it's here. In OWL Accord display, you have a network preview. So it's a very, I mean, not great, but it's some tool to visualize the network. So this is the network as it is here. You can change the seed and you will see that the weights are visualized here, right? So there is 2 neurons in input, 3 neurons in here, and 1 neuron in here. And then the weights are just randomized. But after training, this is changing a bit. I mean, right now it's not changing because the iterations is just 100. We need a bit more. So let's increase the iterations to 10,000. Right? And you see that the weights actually changed. Right? So we can actually, it's such a small network that we can actually animate it with a slider, right? And you see that the learning actually happens with that visualization. And the error is also dropping down. So, I mean, there's a mistake, but there is no iterations. But for the first iteration, the error is 0.9. So it means that it was supposed to be 1, but it's 0, more or less. But if we increase it, it quickly drops down to 0.4. And then it takes a lot of time to get to 0.28. Now, this is very important to remember that this is just the way the neural networks will always be trained. So, yeah, maybe we'll discuss it later. I mean, I don't want to obfuscate it right now. So anyway, this is how it works. Initially, the network takes some time to just jiggle the weights a bit. But then when it's on the right track, it drops really quickly, like the error. So it improves very quickly to some point. But then to get it from 70% accuracy to 90% accuracy can take days or hours, right? So very quickly gets the first basic, boost. But then later on, it's a very slow process. So the learning rate. So when we have the backpropagation, right? So we change the weights. If we compute the error and then backpropagate the error and change the weight so that the output will give us exactly the right value for one case, we will never be able to optimize the network. So in the end, teach it about all the cases possible. It will learn about the first one, define the weights so that it produces the right output for this first case, but then for the second case, it will produce some garbage, so we'll again adjust it, but then it will break the first value, right, the first case. So to do that, we need to introduce the learning rate. So the change to the weights whenever you backpropagate, right, so propagate the error backwards, the change has to be just very small, right? So usually it's 1%, right? So we take 1%, just like here, 1% of the value. In this case, because we have a very small network, very small sample size, it's actually just, it's a toy problem. It's not even a toy problem. It's very, very small. We could even increase the learning rate to 0.1, right? But let's leave it as 0.01. It's just, it's better. Like 1% is usually the value. Even in very complex networks, which I saw, it's like 1%. Momentum is, yeah, let's discuss it later. Epoch later. So iterations is how many times we pass the values forward and backward, right? So that's the number of iterations. And you see that even with that simple problem, because of the learning rate being so small, we have to do it 10,000 times to have some meaningful outputs. Now, how does this translate to what we expect the network to do? We'll get at a component which is called Aula Accord, network, compute. And now when we have this network trained, right, I can give it any input and get the output. So I expect that if I give it 0, 0 as the input, I will get 0 as the output. So let's try that. Let's go copy those components, right? We'll do it just in a smarter way in a second, but this is the fastest way. So let's check it. Or actually, I'm sorry, this should be the way. We get this tensor set and we put it as the input, right? And then we de-tensor set and we'll see the 4 tensors, right? Okay, so you see that the values are, instead of 0, 1, 1, 0, they are 0 0.1, 0 0.48, 0 0.88, and 0 0.52. So they're kind of right-ish, unless, I mean, the first one and the third one are wrong because this one should be higher than this one. What it means is that we are not training for long enough. This error is still too high. If we start from the very beginning, right? So if we start with the first iteration here, you can see that all of those values are 1. So over time, as we increase the iterations, you can see that those values get closer and closer to what I really wanted to do. Okay. But as you can see, it's stuck. So let's try to do 10 times more, 100,000 iterations. Okay, I think we must have a mistake somewhere because this is averaging out with this. There must be a mistake somewhere. Okay, the mistake is that we don't have enough neurons, I think. I think that we don't have enough neurons right now. Yeah, it's probably because we don't have enough neurons. And this means that the data is just getting squeezed and averaged in those 2 cases, right? So it might just work if we change the seed. yeah, so you see that depending on the seed, so on this initial randomization of the network, it might or it might not work. But to guarantee that it will work, we need to introduce just one more neuron in this case, right? And then I hope that in every case, it will always work, right? You can see that it's 0.01, 0.9, 0.9, and 0.03. I will increase the network size, so 2, 4, and 1 neurons, right? It's getting a bit better. And now when I change this, right, you can see that it's always resulting in a good outcome, right? So that's because I think that the good analogy of what is happening with the network is a bitmap, right? So, or a camera. If it has enough resolution, enough pixels, it can see more details, right? And if there is not enough pixels, then the information which is supposed to be in 1 pixel is getting averaged, right? So we have no contrast, or so it's like it's a very abstract analogy, so don't get it, uh, don't try to map it to the backpropagation and so on. But the thing is that the size of the network is somehow like resolution, right? The more neurons, the more details you can catch in the data, right? But there is a catch in that. So if you introduce too many neurons, I mean, first of all, you of course have a long training process, right? So that's the one like not really a bottleneck, but one issue with huge networks. But second of all, if you have too many neurons, it will start to consider noise in the data as important information. So yeah, it will be like it can overfit basically. We'll talk about all of that a bit later, but you cannot just crank up the knob and expect it to always work, right? That's basically the point. We have to have a good understanding of why it works that way. In this case, when we have 4 neurons, I expect that even with 10,000 iterations, we should be, not really, 10,000 is not enough, but 20,000 should be fine. Yeah, this is correct, right? So when you are training the network, you stop training when more or less everything is fine. You never overtrain, right? Because when you overtrain the network, like we do with 100,000 iterations, it's so close to the input values that it's said that the network is memorizing only those 4 cases, and then everything in between is getting lost or getting averaged in the wrong way. We'll visualize it just in a second, but this is just to say that you never really want to get to that precision where you have everything to like 1%, right? Even that, like 0.03, that's too much. Like it's too much. This is just fine. 0.9, 0.1, that is correct, right? We don't overfit, but it works in all the cases, almost all the cases. Like here, we can figure out, round up the value, round down the value, and see if it's correct. Okay, but this problem is really nice because we can actually visualize the entire function of the network and analyze it, and then figure out what are the parameters and how they affect the function. So as you remember, or maybe not, let's visualize it, then we'll have an analogy with what we had in the first part. So I just want to delete that. And in the input here, you see that I'm inputting just the binary value 0 or 1. But the truth is that I can have 2 sliders and construct tensor. And then, or maybe tensor set right away. So tensor or data tree to tensor set, right? This will be easier. And this is our data tree. And this right away, it packs this tensor in a tensor set, right? And I can put it here, right? Now, the thing is that the neural network never really saw this kind of input, right? So it never really, like in the data set, we only have zeros and ones, but I'm asking it to generate the output based on those two inputs. So the tensor set. So what will it give me? What is the value of the tensor? 0.24, right? So I'll try to change it just a bit. Now you see that it's going in the right direction, right? We are getting closer to 0 and 1, and this is getting closer to 1. If I change this, right, you can see that it's getting closer to 1. So it has good understanding. Now this is the power, like this in the essence is the power of neural networks, that they are really good with noisy data. They are really good with generalization. So, you know, this generalizes, right? This is exactly generalization. Instead of zeros and ones, I'm asking it for a different thing. It kind of maps it to the knowledge which it already has, and it tries to guess what would be the correct value. And this is what is happening right now. Okay, but I'm playing here with sliders, but what about creating a range and an entire grid of points, right? So construct points, cross-reference, like that. Let's put like 30 points here, so it will be like 961, right? And here we can use the feature tensor set. So we have two features, right? So x and y coordinates, right? And this is our tensor set. Now, if I put that tensor set instead of this one, I will have 961 inputs, but that's fine. It will take no time to compute. And I have those values now here, right? So let's try to visualize it. I'll get the d-tensor set. So d-tensor set, or actually, let's get the tensor set to data tree. So this is this one, right? I will get the data out, and I have just numbers, flatten the numbers, and let's get the XYZ point. So construct point, and let's put A and B just like that, and then the output here. Okay, let's zoom. And now we can see this is exactly what we were after, right? We want to visualize the entire function of the network. This is the entire function of the network, right? All the possible inputs which are, let's say, reasonable, which is between 0 and 1, they get mapped to some value. And this is exactly what the neural network is learning. Now, when we have this visualization, we can go back to teaching and we can see what it means to learn, right? So, of course, we have this one visualization where we see how the network is changing, but it's not really giving us a lot of information. On the other hand, this gives us a lot of information here. So we'll try to start with 1. Usually then the freshly initialized network will always output just ones. That's just how it works. And you can see that over time, it tries to fit into those 4 input points. So, you know, 0, 0, 1, 1. And this is just how it works, right? And now overfitting is kind of here. So overfitting means that this transition between 0 and 1 is just too steep, right? It probably does, it's quite rare in real world to have data set with such steep transitions, right? So we could even probably go with, 1 second. I want to overfit it even more. Yeah, so maybe let's put. So it's quite rare to expect this kind of data, right? Distribution. It just overfit. So for, you know, for the values in between, which we expect to be smooth, it actually creates either 0 or 1 or nothing, like almost nothing in between. So this is what overfitting means in this context, right? We will want to have something like that. And this, you see that for the X and Y, 0 and 1, it gives the proper values. It's high or low. But for the stuff in between, it gives something which looks reasonable, right? It's not like all the, you know, very steepy cliffs and and very dramatic transitions, right? So this is this one. Now let's go back to our very simple network and let's try to fail the training. Okay, so this is what it looks like when it fails. For those two inputs which were supposed to be different, it just generates 0.1. It considers it as an average. So the smaller the network, the less detail of the data set it will convey, right, or learn. The larger it is, the more detail it will learn. Now, what it means is as well, when we have, let's discuss two big networks, right? So network which is too big, let's say that this is our data set. Let's try here. This is our data set. Some graph. Right? So this is our data set. And the network which trains correctly should go like that, right? Every outlier here is just an outlier. We have to consider it noise, right? It's because if you have too many neurons, your network will go more like that. And just the more realistic curve is actually this one. You know that in statistics, there is never, there's always some noise, right? So we assume that those deviations from this curve are just noise. And by changing the size of the network, we say what is basically the tolerable noise, right? So if we have a large network, we say that nothing is noise, right? And then it's incorrect, because in real life, real world, values are always noisy, right? Yeah, so we have to have a network which just blurs it out, but in that way, it averages it in a smart way. In a smart way, meaning that it follows peaks and bottoms, but it's somewhere in between, right? So we know that this network doesn't have enough detail. So what our network right now does is like that, right? Doesn't have enough detail. It just makes a straight line instead of some kind of a curve. This is exactly here. So if I make 4, there's just enough neurons to give me all the detail I need, but also without overfitting, right? Okay, so this is one thing. Let's have like a 15-minute break. And after that, we'll discuss how the networks are visualized in TensorFlow and in other frameworks. We have we have other frameworks, but they talk about networks in a completely different way, which got me really confused when I started learning that. So I just really want to tell you, like, if someone wants to do the TensorFlow, it's good to understand what is going on in there and why they are not talking about neurons at all, right? So this is after that, and then we'll try to get to some more concrete example. That will be for the end of today. Boxes, recognition of boxes, classification of boxes, or something like that. Yep, that will be the plan for today in that case. Okay, so like, let's
Great.
meet at 5.
Yep. Cool.
Okay. Can you hear me?
Yep. Yes.
Okay.
Yep.
Okay, let's share the screen again. Okay, so back to the network. We'll talk about like learning rate, momentum, and yeah, and how it relates in TensorFlow. Because I mean, if you are not going to use like TensorFlow or any other library for machine learning, you can skip it. But for those of you who would like to relate this to what we are doing with what is in TensorFlow, yeah, so TensorFlow or any other of those libraries, like big neural network libraries, they will always consider, or very often consider, a neural network as, yeah, not to scare you, a hyperdimensional point. So what it means is that when we have a network, we have some neurons like that, right? And we have those weights, right? So each connection has a weight. Now, if you were to take all of those values associated with connections and write them down as a list of values, right? This becomes a vector, right? So it's basically a list of numbers. And if you were to interpret this list of numbers as coordinates of a hyperdimensional point, so in our case, it's 1, 2, 3, 1, 2, 3, and 1, 2, 3, that's 9 dimensions, right? If you were to consider this list of numbers as coordinates of a 9-dimensional points, again, skipping the bias because that's not the point right now, but 9 dimensions, then you can consider this entire neural network as a hyperdimensional point. Now we will go back to this still, and I will show you why is it good to visualize it like that. So right now we've been always talking about neurons and how they work, how they relate with each other, and so on. But forget about it. It's right now we are just considering a neural network as a hyperdimensional point again. So in this case, if we'll take a look at this demo on this tail, how momentum really works, this point which you are looking here is it's a representation of a network which is getting trained, right? So step size A or alpha is actually the learning rate, which we have set to 1%. Here it's 2%. And momentum, yeah, so momentum, we'll discuss it just in a second. So you can see that the step size, if I have a small step size, then it takes really a lot of steps to progress the training, right? So there is some optimum. So there is some target, who knows where, neural network, which gets all the answers correctly, right? And it's just ideal. So when we are training, we are moving towards that optimum, right? So we randomize the weights. So we randomize the position of the initial point here. And training is just getting us closer to the optimum. Now, step size, as you see, can, the bigger the learning rate, the greater the learning rate, the faster it gets to the optimum. But at some point, you can see this, if we have a step size which is big with no momentum, just no momentum, right? This is what can happen. So this is no momentum, right? And you can see that the problem is that with a randomized starting point and no momentum at all, the neural network will take, huge steps, and then at some point it will get to this point, but it still will not get to the optimum. That's because, it just misses the point, right? It misses the right spot, right? And it never gets there, or it will take a lot of steps to get there. Or it will miss it at all, like it can jump back and forth around the optimum, never really getting there, right? Now with momentum, maybe we can move it here. Yeah. With momentum, we get some of that previous change added to the current change, right? So we store the previous values for the network, we change the values with backpropagation, we have the new values, and somehow we average them with those values from before the change, right? Or even before the change, it can, you know, have a couple of steps before, and that is called momentum, right? So momentum, you know, momentum in physics is basically when you push a body, it keeps rolling, right? Because it's momentum, and here it's the same. We push the network, and it keeps rolling in the same direction with, you know, with some change, right? So when we increase the momentum, you can see that overall, the final solution gets way closer to optimum. And also, if we start somewhere here and make the step size, not just like that, right? So no momentum and momentum, right? It gets really close to the optimum with the right parameters, right? Of course, if the momentum is too high, this is just exploding. Like, it's not the same, but you can, if you remember Kangaroo 1, and if you have springs in Kangaroo 1, they also had some kind of momentum, and sometimes the simulation exploded, right? That's more or less the same. I mean, the same phenomenon of the incorrect momentum, and then just, you know, everything goes wrong at this point, right? And this is just, you know, it's not even working, right? So yes, so with the right momentum value, with the right step size, we can get really close to the optimum, and this is really important. So by default, momentum should be more or less 1/10 of a learning rate, right? And I think it's the same here. Well, no, it's actually not the same here, but if our learning rate, yeah, this is just a different, okay, this is not really meaningful. Learning rate is usually 1 to 2%, right? Momentum should be 1/10 of that, more or less. If it's too much, then you saw just what happens, right? If it's too little, then it doesn't really do much. So it has to be just right, and just right is more or less 1/10 of a percent. Now the epoch, and this is something which I have to check, but when we do the backward propagation, right? As I said, we forward one signal, like one input, we get one output, and then we back propagate. Now, usually when it's like real world application, you do it a bit differently. You actually forward, let's say 10 examples, and you average the error in the end, right? So, or accumulate the error, doesn't really matter. You average the error in the output, and then do back propagation once. So every 10th sensor, you will do the back propagation and update the weights, but you will 10 times feed forward and collect the errors. I'm not sure if it works with Awkward.net. It's implemented here, it's in the code behind, but I'm not really sure if Awkward.net actually does it in this version. I think that last time I make a couple of those machine learning workshops. I remember it wasn't working, but last time it actually did change something when I changed it. So we'll see. All in all, if epoch is 1, it's just gonna be slower. That's what it means. So if we update every time we feed forward, it's just gonna be slower. And yeah, that's more or less it. It will not be incorrect, let's say. Now we have network. Okay, so let's go back to TensorFlow. Just one more thing about TensorFlow. We have in TensorFlow, the most important thing is the optimizers, right? So is it here? No, that's just the neural networks. Where is it? Types. I haven't been using this for like a lot of time. We should just use the ADA. Yeah, anyway, any kind of optimizer. So, yeah, So here we set the learning rate and momentum just once, right? We just figure out what is the value. We set it once and let it run for a while, right? And it eventually gets somewhere. But in TensorFlow and other libraries like Keras, for instance, you will see that there are some other optimizers, right? So the thing which we use in here, the fixed learning rate, fixed momentum, that's more or less SGD. SGD, which is stochastic gradient descent, right? With momentum, just like here. But, and this is the method, right? So we put the point, we put the neural network somewhere, some values, backward propagate, we change it with its learning rate, and it's done. But let's say with AdaGrad, what do? We have a couple of different, or maybe Adam is a bit more. Yeah, what we have is a couple of different parameters in the input. What it usually does is it can change the learning process and the learning hyperparameters like the learning rate and momentum depending on what it is actually achieving, right? So if the optimizer sees that there is no change or the change is very small, but it goes in the right direction, it might speed up the learning rate, right? Or slow down if the changes are too big. The details are here, right? So we can read the detail in details what those optimizers do, but eventually what they want to achieve is just faster and better accuracy, right? So those what those optimizers do. SGD is just fine for our applications. Now, yeah, so why gradient descent? Because we have in this distill demo, you saw that we have this gradient whether it falls down or up to the optimal position, right? So that it follows some gradient slope of this optimal path. So this is how they perceive it, and you will never like you will see some neurons, but here on this page where we have a description of optimizer Adam, there is not even a neuron name, right? It just like not even hyper, like it's yeah, it doesn't even say anything about neurons at all. So that's why it's confusing at first, but then when you understand that it's moving this neural network in this huge hyperdimensional space, it becomes just kind of obvious. Okay, so we have this demo. Now let's move to some concrete example, and we'll just use all of the knowledge now to make a very simple classifier. So now it's in this case, what we are doing, we're actually doing regression, right? Because we have one output and we expect to see some kind of floating point value in this output, right? So I try to estimate what will be the value for each of those input points, and I visualize it as Z. And I ask the neural network about the precise value. Now, so this is more or less regression, but what we will do, we will have, let's say, a collection of boxes, right? And I will have different classes of boxes. So I'll say it's a tall box, it's a short one, or wide maybe, wide, and another one will be long, right? So I'll have 3 classes. Maybe we can have a cube as well. So it means that it's more or less equal in all dimensions. And so what it means is that our network will have 3 inputs. Yeah, that's right. So X, Y, Z, or width. Maybe we can do this as width, depth, and height of each box. And then there will be 4 outputs, right? So, and there will be some networking here, right? So there is connections here, and I give it the dimensions of a box, and it tells me what is the box. Is it tall, wide, long, or cube? And in this case, we expect, well, one or maybe two values highlighted, right? Maybe there will be a case where it's a cube, but also a tall cube, because it's a big one. So the dimension, the z dimension is like the height is tall. So it might be classified as tall and cube. But in the end, we expect the neural network to tell us what is the highest value in the output, right? So the highest value will interpret it as one of those descriptions. And in this case, it's a classifier, right? So there are 4 classes, and it shows us what's the class. So this kind of neural network, let's say that, okay, so maybe first of all, classification with neural networks, right? Classification neural, most common, like the most thing which we will always see will be about images. And you know, people always wanted to have, I think ImageNet is the data, right? So you know, there is a database where the neural network will will learn if it's a picture of a dog or a cat, right? So there is a database of dogs and cats, and it will try to see what is in there. Like, of course, the network it's a bit more complicated, but more or less there are, of course, neurons in there. They are organized a bit differently. There is way more of the neurons, but in the end, you have input image and output class, cat or dog. So instead of 4 outputs, you have 2. And then you always see this percentage, right? So 14% dog, 85 Elon Musk. That's it's a joke, but the point is that the neural network will never be really sure what it is in the image, right? Or almost no. Like, you always have to have a threshold value which will tell you, okay, I can classify it as a dog or a person. So it will be probably something like 0.8, right? So 80% sure, it means that this is a dog or something like that. So always rounded. It's never crisp, it's always like fuzzy, right? So yeah, you can see we get to 98.7 accuracy in this case with, yeah, anyway, don't worry about this network yet. I mean, we'll talk about convolutional neural networks if we have time. You cannot really do that with OWL, but you can do it with TensorFlow, and you have like ready-made examples. Yeah, so this is the classification. This is what we want to do. Now, how does it work with design? So I have, I'm not sure if I will be able to show you, but I'm teaching at IAC for a couple of years right now, and this year the students really went deep into that classification and also labeling of designs. So what we experimented with was labeling different designs and seeing like what would be the label or what would be the name for the design which a person would name it, right? So let's say it's a tall design, massive, dynamic, and so on. And we try to map that to the parametric model. So we have a parametric model of a chair. I'm just not sure if we have it on the blog. Yeah, it's here. Right, so this was one group. And just to show you that it's not just about boxes, right? It's more about like, how do we design and what would be the future of design eventually if we get everything right. So first of all, we created, the students created a survey. And in the survey, they were asking people which one of those images is the most really like different from each other. It's not just one variation. Then they made the parametric model of Rietveld, and they made this Rietveld. And they also asked people about what do you think about, yeah, my internet connection is unstable. Anyway, what do you think about this chair? which one of the chair is the most massive one, which one is the lightweight one, dynamic, open, elegant, and calm, right? You have all of that here. So and now the experiment was to map images to designs, right? You can see that we have the same characteristics. And the idea was that we can select a couple of images. Those images will give us those characteristics. And based on those characteristics, we will design a chair, right? So they're designed by choosing photos, basically. However strange it sounds, I think there is something really fascinating about that. You can imagine that you can generate like if we were to continue with that, right? It's a student project, but if we were to make a research project out of that, it would be really interesting to like scrape someone's Facebook wall of all the images and just generate design based on that. And this will be like mass customized, personalized design for that person based on the images or maybe words, right? Here it's images, but it can be anything, right? And there is like weights, different designs, mapping one to another. But yeah, it's let's say this is generated with OWL, right? So everything with OWL, and I think that's yeah, you can see there is some correlation here with the actual designs. Yeah, there are some successes. There are some really things that should probably work a bit work a bit more, but I mean, if you ask me, this one is way closer to the black square than this one, and this one is way closer to this one than to this one, if you ask me. But I mean, it's very subjective. But that was the point. We wanted to work with subjective data. So we wanted to see what can we do about that. And they have like a lot of studies, how would we use that. But anyway, and you can see that this neural network is nothing really strange, right? Like it's nothing really more complex than what we are doing right now. And I will eventually maybe link this to you. And like we have another like consultations next week, but we can also move it in time. I mean, we have to talk with Vijay, or like whether you want to have some more time to do something, and then we can have like a review. Maybe I can point you to some other websites or examples, but this is a good start point. I think this is a really good example of what can be done. Even if it doesn't really work, I think this is a really good step forward. I think some parts work, some parts do not work. Mapping the design to words was fine. Mapping images to words was not so great. So yeah, well, let me see if we have some other example from there. Was it MAA or MRAC? I think it was MAA. Yeah, I can't really tell which was the program. I think that they are additions. Nope. MRAC 01. Yeah, I'm pretty sure it was actually MAA, but can't find it right now. Anyway, this one, which is AI generated furniture, maybe you can take a look at it. Yeah, it was program MRAC. Or here's based on the course. Yeah, so this was one. Nope. I just wanted to show you one more. What was that one? Oh no, this is not a good example here, I think. Just a second. Sunflower. Yeah, this one is another one. Yeah, so this one is a bit different. Here they were using very similar descriptions of design to generate the design, right? So we were experimenting both with inputting words, outputting design, or inputting design, outputting words, both directions. And we tried to train the neural network to recognize different designs. And again, we have a survey. We ask people what they think about designs, and then we try to generate a description for a design. So, the idea is great. Like, you have design as a designer, and you don't have to ask people what would they think about it, if you were able, of course, to collect a lot of that information. I think that this might be potentially like the future of like some really creepy but successful way of not really, I mean, marketing more or less, right? You know that Facebook already collects a lot of data about you, but it doesn't really collect, I mean, or maybe it does, about your design preferences, right? But what if we were to collect this data and even like, with, of course, with agreement of the people which are analyzed, right? But if we were to collect this data, maybe we could design better, right? Because as you know, the average person with no understanding of architecture or design will have a hard time coming up with a good design description, right? But if we analyze that person from that point of what this person likes, maybe it will be a good, at least a first indication of what could be done, what we could do as designers to make this person satisfied, right, with our design. So this is, this is like one of the approaches here. In the end, they ended up with making sure that the curves, as we describe them, are what they are, right? So mapping the description to the curve, and then training the network. So this animation is actually training the network over time and seeing how well it fits the data. And then I think they have this really nice example of actually, just a second. I think it's, yeah, so here they are asking the network to generate a dynamic and spacious curve, and it creates this curve. Now, is it really working? That's, I saw it generate some really interesting examples of things which are actually like tangible. You can see that it works, right? But sometimes it doesn't work. Now, why it doesn't work is probably because we don't have enough data, right? So we are just scraping the surface, and it will probably take some more time, some more research on our side to collect enough data, to create databases, and then use this knowledge which we are seeing here to actually get it right and get it like working for us actually, right? This is just sketch, and I never expected to really work. But if we see some good, like at least non-random is crucial. If we see non-random results from that, it means that it might work. And if it might work, we have to do that. Like, we have to try it out, right? So this is like a first step. I consider the first step. It kind of works. And of course, it will require quite a lot of refinement, but it's getting somewhere, right? So you can see that we have different examples here. And calm, right? I think they are mapping it from 0 to 10, but this is just evaluating different training. And you can agree with that or not. Maybe the encoding of the curve or the how we describe the shape could be different. But the point is that in some cases, it seems that it's not random. And this is really something that gives us hope that maybe we'll get, with more research, we can get somewhere with that, right? Yeah, in one way it works, in the other way it works better. So other way, which means that we have an input curve and we try to describe it, actually, as far as I remember, work better than inputting the words and outputting the curve. We can discuss it a bit later why it's like that. So as you see, we'll start with a box. It's a very simple example, but I want you to just have all of the other stuff in mind and maybe try to think about your designs and then come up with questions next time we see each other. I mean, tomorrow we see each other, but for a different exercise. But the next time we talk and we have a review, maybe you will have some ideas. What could you do with your design, and yeah, and how to use that knowledge. Yeah, right now I'm kind of on a standpoint where I think that we need to collect data first of all. So I'm making a lot of user surveys and just asking people what they think about designs. At some point, I mean, there has to be a critical mass where it actually starts to work. I just want to know where it is. So yeah, boxes. Let's create a couple of boxes. I will create again a panel, or maybe we can create the boxes in Grasshopper, or a panel. Let's do a panel. In that way, I can send them to you and you can use exactly the same ones. Okay, so this will be a tall one. So I will describe all the dimensions from 0 to 100. And then we'll see what we have to do to make it correct and make it compatible with the network. But anyway, 100, 110. Let's have like 3 examples of each. So 20, 30, 100, or 80. This is tall guys. So tall, wide, wide, tall. And then we have cubes. So cube. So cube will be 100, 100, 100, as well as 10 by 10. Then we can have another guy. I mean, usually when I do this exercise, I draw the boxes in the viewport in Rhino and then reference them to Grasshopper. So if you know how to do it, you can do it that way. But this time, let's just try to do it that way so that we can get exactly the same results, but also we can think about those parameters a bit more. Then another one will be long, right? So long can be in both directions. So it can be 100 by 10 by 10, as well as 50, or let's say 10 by 50 by 10, right? I'll add some more. So let's add 2 more for each. Okay. Now, question is, how many should we have? We should have enough so that we know that it works. I mean, we have to test it. So usually, yeah, so in this example and all the other examples, we are doing everything wrong. And this is on purpose. I mean, when you train the network, as we said before, when you have all of those samples, you want to train it with, let's say, 75% of them and test it against those. We have a shortcut here that we are actually testing, like running it here and just testing it with some input which we make by hand. It's enough for us. But when you actually get to like do the real thing, you have to take all of this data set and split it. Just use the split component, split tensor set, and split it with like 80 to 20%, and then evaluate it against those 20%, right? So you train it with those 80, evaluate against 20, visualize those 20%, see how well it performs. This is how we know that it actually learns. I mean, when you don't do that and you just evaluate it against those examples, there is a small risk that it will just learn those examples and it will not be able to generalize. But with those very simple networks which we use, that's hardly the case. So we have 10 by 10 by 100, 20 by 30 by 80. Let's say that we'll have 50 by 50 by 90, right? And another one which will be 10 by 50 or 40 by, let's say 80, right? This is also tall for me. Then we can have this one, which will be 50 by 50 by 5, let's say, and 80 by 90 by, let's say 20. Now cube, I mean, that's quite easy, but we can also have some variation, like 25. It's close to cube, right? Then we can have another one which is 50, 45, and let's say 60, more or less. And then the long ones is this guy. It can be also like 100 here, 20 here. Of course, this is completely like fake data, right? And we know that it's fake. We make it by hand, but we make it by hand so that we can understand fully what is going on. So we have those guys, and now we need to merge that. I mean, that is quite a tedious task, but let's try to merge it. So 1, 2, 3, and 4. I'll have 4 merge components and then 1 merge to get all of them. Right, 1, 2, 3, and 4. 2, and 4. And then we can have another one to couple all of that. Right, and we have the numbers here. Yeah, we should probably, okay, that's not smart. But anyway, is it partition or is it, yeah, I think it's partition, right? So we can do it that way. I should graph those inputs or just create a data tree, but this is easier. We just partition by 3. And you know that in chunks, you will have a data tree where each triplet is just one of those, right? Now we have to, yeah, so we have to create a data tree to Tensor Set component. And we need to like fabricate as well the outputs, right? So we have 16 tensors here. We need to have 16 outputs. So I would say that we need 4, 4, 4, and 4. Again, it's easier to do it by hand sometimes. So I would just do 0. How to do that? 0, 0, 0, 1, 1, 1, 1, 2, 2, 2. Yeah, something like that. That is fine enough. If it works, it works. Now here we can graft, and again use the data tree to Tensor Set. So this will indicate which type the building is, right, for outputs. And this is all we need for the data set right now. Let's put it here. Okay. Now, what is the problem right now is that we always assume that the data has to be normalized. So normalization means that values in all dimensions are between 0 and 1. Why do we need to do that? Is because we have, if we have a data set where there is a huge difference between those parameters, so let's say that the width is between 0 and 10 and the height is between 0 and 100, neural network doesn't understand that there are just different ranges. It will think that the difference in height is more important than the difference in width, right? If there is a smaller difference in a data set, it will think that the most important is the difference in height, right? So the broadest range, the range with the highest values, will be the most important. So to equalize the importance of those parameters or features, you want to make them equal. So basically normalize to 0 to 1. Not to say that the only thing which a neuron can output is actually 0 or 1, right? Or -1 and 1, depending on the sigmoid function, right? So it's good to have the inputs and outputs in the same range, more or less, right? But you can see that the sigmoid function never really gets, I mean, here it's 1 and 0, right? Or here it's -1 and 1. Depending on the function, we will have different outputs, but it's always somewhere in the range of 0 to 1 or -1 to 1. So we need to remap Tensor Set. And we know that our source was always from 0 to 100. Now, sometimes I see that students take the component which is called Tensor Set bounds. It works just like bounds, right? So you know that bounds will take the values and it will output the domain. But the problem is that this domain in a data set is actually fixed. And if you change it, the neural network will not know what is going on, right? So you want this source domain always to be fixed. Target is 1, okay? Exactly the same tensor set. This guy, on the other hand, oh, it's actually incorrect. So this guy, on the other hand, we need to change it. So right now it's incorrect because it's giving us like 16 values, right? I mean, it's just one. Again, it's actually incorrect. So this is what I would do for. I mean, first of all, the neural network cannot output 3. That's one mistake. The other mistake is that the output is not 1 value, but 4 values, right? Go back to our image of the network. We have 4 values. We need 4 values in the output. So each tensor will be composed of 4 values. It will be like 0, 1, 0, 0, or something like that. So for that, we need to use a different component than data tree to tensor set. This component is called one-hot. So one-hot is a notion. One-hot is a notion in digital circuits and machine learning. One-hot is a group of bits among which the legal combination of values are whatever. Single high and all lows, right? So those are one-hot outputs, right? What it means is that the neural network will indicate that there is one class valid for our output. And instead of 0, 1, 2, 3, you will have 0 as 1. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 2, 1, 0, and then 0, 0, 0, 1. So this will just change the tensors. So hot is the integer, right? So we need to indicate which value is hot from those 4 outputs. And we need to do it that way. Length needs to be 4 because we have 4 cases, right? And then eventually we have hot value, it's just default 1, and the cold value, which is 0. Doesn't matter. But sometimes maybe you want to change that. And in this case, we have, again, we don't have to graph, we can just put it directly here. We have tensor set with 16 tensors. And if we deconstruct tensor set, you will see that each tensor is composed now of 4 values, right? And they are matching this pattern. So 1, 1, 1, and 1. Yeah, so this is the output which we want to get. Again, the input, on the other hand, is this one, right? So those values are here, those values are here. Input, output. It doesn't matter that the output has more values than the input. You can have as many inputs or outputs as you want, up to you. You can have one input which generates 100,000 values in the output. Doesn't matter, or the opposite. So this is what is really nice about neural networks, that you can, function is a map, right? So you can create a mapping between as many parameters as you want. You don't really have to worry about that. Anyway, we don't use that. We just use tensor sets as they are, input, output. And this time, let's do it with anemone. It's not really necessary here, but let's do it with anemone. So loop start, loop end, and we'll just put this here. Now, our data is not actually the tensors, right? They don't change over the time. Our data is our network. So let's construct network. I think this is the one, right? Yeah, this is the one. So we construct the network, and what are the layers like? Here I made it so that you have 3 inputs, 4 outputs, but there is something in between. We'll guess it. So 3 inputs, 4 outputs, and something in between. So it's often that people ask, how do you get this input? Like, how do you get this middle value? So there is, it's a guess. So first guess should be more or less from those 2 values. Maybe you can have an average and then round it up. So 3 and 4, it's 7. By 2, it's 3.5. So maybe it should be just 4. You train it once, you see if it works, and if it doesn't work, because you see that some values are not distinguished between each other, just like we saw with the Xor function, that 2 points became 0.1, 0.5. If it does something similar, and it cannot distinguish between particular values, then you just increase this number. So that's one way. The other way, most of the time, if you take the higher value from those 2, multiply it by 2, that will be way more than enough, right? So this is another formula which you can always use. In some other cases, you will just want to have, like, if you have 4 inputs, 4 outputs, it's obvious to do like 4, 4, 4, right? Maybe 4, 8. Like you just need to test it, run it, test it, and then refine it. In fact, not really. It's you never really train the neural network once. You train it multiple times, maybe not to the fullest, but you see how it performs over after 1 hour of training. You change it, train it again for 1 hour, and see if it's better. And then you understand that the change which you just did is in the right direction. So let's say you increase the momentum. So you try to increase it again, and then it probably gets worse because you just saw what happens if the momentum is too high, right? So then you just decrease it. And yeah, you just need to be able to identify what are the problems which emerge after you train the network and how they are dependent on those input parameters, right? So yeah, so this is it. We'll get a better understanding once we visualize the training here. But anyway, this is our architecture right now. Everything else is the same, default. And here we have the backprop. Our data is the network, right? And the inputs are here. The outputs are here. Maybe we can take the opposite. Okay. And this time, because we have a loop, I'll increase the iterations to 1000 here. I mean, nothing really more, like we don't have to change anything else right now, but iterations is good if it's 1000 here. And let's make a small trick here. Let's add 1 more input to anemone. Let's create a merge component. Let's do that. Okay, so in the D1 output, let's flatten here. I'll collect the error value, right? And I'll use quick graph to monitor the value. Okay, you will see how it works in a second. Now, let's increase the repeat to 100 and let's just run it. So now 100 times 1000, that's 100,000 times. Seems reasonable, right? And yeah, this is just how it works. You can visualize the error. So the error was 2, it got to 0.002. It means that it's very close to the real thing. It's overfitted quite a bit, right? But the most important here is that this curve, for whatever neural network-based learning you will ever do, with whatever neural network you will ever see, will look more or less the same. It's always gonna drop. So we can see it again. It's always gonna drop really quickly down. Like it will take some time to like stabilize in the first place. Like here, it was more or less this value. And then it quickly drops down. And then this last bit takes the longest time, right? Even if you take something really complex, like, you know, the AlphaGo, right? The AlphaGo was the algorithm which beat the human in playing Go. Even if you take this one, even if you take this one, even if you take like super complex algorithm, you will see exactly the same curve. Here they, instead of measuring the, oh man, instead of measuring the error, they measure the success. So it's the like curve rotated upside down. Oh, come on, I want to open this here, right? So it's a curve rotated upside down, but it's still the same characteristic. It dramatically goes up or down in our case, and then it slows down, and this takes a lot of time. So getting from here to here gets the longest time, right? And here it's very easy. The same here and the same here. No matter if you're using, I mean, I don't know what they are comparing reinforcement to supervised, but anyway, in most of those learning things, like learning algorithms, you will always see this kind of, you know, curve, like learning error curve. And yeah, so ELO rating is actually the chess rating, right? So if you play chess, you have the ELO rating, and this is just comparing it to some, I think some other people as well. And you can see that I think this one, the Lee one, is the one which beat the master of Go, right? And then it gets even better, right? So anyway, but this curve and this curve is the same, right? More or less the same characteristic. So if your training process, let's say, we slow it down, right? We run it again. Okay, so that's an initial drop, which is in the faster.
It seems to that we lost you.
So let's do 50. I just want to see like a bit bigger change in here. Yep. It's just going down like crazy, right? And then at some point, use the 70 again. At some point, it will just level out and go in like horizontal, completely horizontal, almost. And this is when we do 1000, right? This 1000, basically the first loop here is illustrating what we've been doing so far here, right? And then it gets lower, and then it gets really good, and then here it's just getting better and better. This is the same as here, right? This period of time. So while in their case, the success rate is the better, the higher the better. In our case, when the error is too small, it means that we are overfitting, right? So it's actually a failure. I mean, not really a failure. It means that we are just training for too long. We don't want this error to be so small. We want it to be something like maybe 0.1. Why? Because if we narrow down the error, the neural network, again, will not average the noisy input. right? Even though we have like a totally synthetic input, it's still quite noisy, right? So you saw that the cube is not exactly a cube all the time, right? So we don't want it to be so specific. We want to have like a more or less probable picture encoded in the network, right? But it doesn't have to be so precise. It's actually the opposite of what we want to do. We want to generalize. So in that case, I'll just leave it with, I think 100 times 100. That's just 10,000 runs. No, that's actually a bit too big error. So let's do 200 here. Let's get to something like 0.1. Yeah, that's not really okay. Let's do 300. Okay, I mean, it's a bit too much, but let's leave it as it is. It's kind of fine, right? It just got to this end slope. So once we have that, we have this network. Now let's see if it actually works. So the easiest way, and again, it's not the correct way, but it's the easiest way to figure out whether it even works at all is just to compute the same using this network. We just want to compute the outputs of the same inputs, right? Again, we are testing it against the same input which it was trained with, so it's not correct technically, but I mean, it's just indication of whether it works or not. Yeah, and you see, we saw that the error is really small, and you see that in the output is, I mean, we get really close to the actual thing, right? Too close, I would say. Let's run it 250. Right, and it's getting too close, right? It's way too close. So let's run 220 or even 200. Let's see if 200 gives us, we just need to have like the biggest person in the right spot, right? Yeah, and it's more or less fine. 0.8 is totally fine to distinguish that this is the good answer, right? Let's leave it like that. Now let's use this network in like with some different data. So right now I will have data tree to Tensor Set here, and I want to have 3 sliders. So from 100, 100, and 100, merge, or actually, yeah, let's do merge. And the result will be divided by 100. So it's normalized, right? Maybe I can just type it here. Yeah, and now we have a tool where we can create a box. So box with domain. Domain box will be fine. I think so. Domain will be fine. Yeah, domain is fine. So we have a box, and the network tells us like what is the type of this box, and it's a cube with a strong indication of the cube, right? So cube, y, tall. Maybe let's move. I mean, maybe we can have a panel where it will tell us tall, wide, cube, and long. And this will be a list of values, right? A list of descriptions will be here. We'll deconstruct it to data tree. So convert tensor set to data tree. Or the other way around is also highest activation will be useful. So highest activation, we will actually take a tensor. And from those 4, I mean, let's put all of them out and we'll see 4 values, but together with their values, right? So index and the values. So we'll see how much confusion is there in the network. We can use the list item with that list, that index, and then put it that way. So we see that it's 80% sure that it's a cube, but also it might be long. Who knows? Again, I'll take those sliders here. I can visualize it in different ways. So let's move. Okay, let's see the cube. Like examine the cube. Let's see if the network now will figure out that something which is 70 by 70 by 70 is a cube. That way we'll know that it generalizes well, right? Because we never showed it a cube which is even close to 70, 70 by 70. But maybe, by some chance, it will learn that rule, right? So more or less 70 by 70 by 70. See, now the input is not even like the same, right? So it's, I mean, we can make it even round and round. Just make it even noisier, right? And you see that it's 90% sure that it's a cube. It's also long, but first of all, it's a cube. And we never showed it this kind of cube, right? So this is why it can be really useful, right? Again, if we now go back to our initial lecture, right, which we started with today, we are at a point where, just a second, I just want to go back to to this first slide today. We have a model which is our neural network. We have some data set, those are our boxes. And now we're asking it about this missing dot here, like what would be here, right? And it knows that it is a box, right? It's a cube, but we are asking it about something which it never saw before. So this is why the neural networks are so great, right? Now let's try to, okay, let's see how it performs with tall stuff, which it also never saw. So maybe we can do like, how would we say that it's a tall thing? Maybe we can have something which is 70 by 20 by 40 or 40 by 20 by 70, which is just a different one. Like, so 40 by 20 by 70, and it's 97% sure it's tall, right? And then it thinks also it's a bit of a cube, but that doesn't really matter. First of all, it thinks it's tall, and we never showed it a tall thing which looks exactly like that, and that's the true power of the neural networks, right? Okay, so this is the example for today. So day 1, 2. Tomorrow we will either continue with that or we'll go straight to autoencoders. Autoencoders also use neural networks, but there is a bit of a twist there, which just gives us a completely different approach to neural networks. Now, is there any question here? I know that we covered lots of information, like a lot of the like hardcore maths, as well as just a lot of information to cover. But maybe you have some like questions regarding what we did today. Any questions?
I have one problem.
Mm-hmm.
Or from the highest activation, the indices are graphed. I don't know why.
You sure you have just one tensor set and one tensor here?
Okay. Yes. Okay. That should be this way.
Yeah.
It works. Cool.
Yeah. Yeah, but you see that it's kind of simple tool, but also it's powerful because you show it some like box and it's just there. But notice that it doesn't really matter if it's a box or a parametric design. You can have as many sliders and input as you like. So you just showed me your designs from your studio. There is like some crazy geometry generated and so on. But even if you have, let's say, I'm not sure about chaotic systems, but let's say that you have some agent-driven like thing which grows, right? And you have some hyperparameters for those agents, like how fast they move, how much they can turn. Those parameters can be input for your neural network. And what do you do with that is up to you, right? Maybe you can decide that particular agent-based thing will be classified by something, and then maybe the choice of the material can be based on those hyperparameters, right? Or maybe you want to do the opposite, like you can you can generate something and analyze it, right? So for instance, analyze what is the surface area of a thing, or the porosity. You can invent as many metrics as you like, treat them as the inputs for the neural network, and get some output, right? The output can be, again, the description of the thing. It can be some design decision which you want to automate, right? So when we had the read film, like one idea which I have right now, it would be really cool to get back to, if we go to those EX students, right? So imagine that instead of like doing all of that, we could have a read filter, and all of those colors and assignment of the assignment of colors to different faces of B-reps is actually automated with a neural network, right? And each face is basically classified with some classifier depending on the input parameters. So you could assign different colors to different B-reps, show it to the network, and then when you change the parameters, it will automatically assign different colors to different faces, right? So this is one way of thinking, right? And then, you know, you have a couple of examples which you like, and then everything in between, it just, the neural network fills in the gaps, right? And it automates your decision process. You might argue it's not good to automate the decision process of the designer, but when you're optimizing stuff or when you have a parametric model, at some point we just need to have those tools, right? Because the person is not, like, even a simple optimization, you're not able to optimize a design which has 100 parameters, right? So you need to have some automation. The final decision may be up to you, but at least this initial decision, let's leave it to the computer, right? So yeah, so this can be as well the color, right? In this case, of course, with more parameters. This would be actually a good study. Like if anyone would like to do that, I think that would be great just to have it. Not sure how close it is to the program of your studio, but it would be great just to, like, you know, make some design decisions based on the parametric model, and then let the algorithm figure out the in-between stuff, right? And then when you change the parametric model, it can automatically assign materials or assign colors, assign, I don't know, even if you have like a modular building, maybe you want to assign different modules depending on some parameters of the overall shape of a building, right? You want to classify the sunniest areas, right? Or the most complex geometrically areas of a facade of a building. That could be, you know, used. You can measure for instance, the curvature of the facade of your, you know, super complex mesh, and based on that, make a decision what kind of a facade should be in that part, right? So very simple example, but I hope that it's clear how it works, and then we can maybe yeah, discuss it a bit later again. Yeah, I mean, yeah, so if anyone has any questions, so this is the time.
For example, yes. Now, if I would like to analyze part of the city, so I can take a geometry, what I have, and then I will just, you know, to sort the domains and put it into the input, right?
Mm-hmm.
Basically, and then I can see what is percentage of the tall and cube and whatever.
Yeah. Of course you can like color code the buildings which are, I don't know, like for instance, there is this entire commune in Denmark which has all the buildings. I mean, I used to live there, and this commune right now is taking part in like a European project about circular economy, because they generated, maybe I can just turn on the camera. 1 second. Yeah, I'm here. So this commune generated a lot of data with BIM models, and they basically have, commune is basically like 3 or 4 towns, and they are, you know, acting together to build the roads and maintain stuff. So they managed to model every single building with some degree of like level of detail in the commune as BIM models. So they have a huge data set of those IFC models, and they have no idea what to do about that, right? And then those kind of tools, I mean, I have no idea how, but clustering, or maybe this could, for instance, sweep the entire data set and pick out those things which have to be corrected. So maybe they would like to read out the BIM parameters. So let's say the age of the building, types of windows, areas of the windows, and then classify it. Is it something which we need to investigate or not? Right? Those kind of tools is what we are going to work on for the next probably decades, right? 2 decades, maybe 2, 3 decades, who knows? But this is something which could be done right away. I mean, not right away, but with some work done. But you know, you imagine that you have, for instance, in Denmark, it also works in a way that they have drones. They actually scan the city with thermal camera on a drone, and they record this, and they investigate where to put more insulation on which building or in which area, or where to change the windows to new ones, right? So that's what they do. And of course, they don't have any tools. That's why they take part in those projects right now, because they don't know what to do with that information. They know it's important to collect it, but they have no tools to do that. Like what to do next is up to us, actually, up to architects. And I think that this could be like a really good example. Like I really think that this example of getting BIM and figuring out, okay, what is the area of the window, what's the orientation of the building, how large is the building, those parameters could be, you know, we could take, let's say, 100 buildings, take those parameters out, and manually, first of all, manually check, okay, which ones are okay and which are the ones which we need to investigate somehow to increase the thermal performance. And based on that, this could then automate this entire process to the hundreds of those houses, right? And we don't have to have a human who needs to go by one, right? This is one way we could use this. It's exactly this kind of network which would do that. Like nothing more really necessary, just processing the data, right? So, yeah, just to give you some ideas. I'm not sure if we have, okay, maybe I can link you this one issue as well. So by report, I'm not sure if it's available. 1 second. I have a really slow connection. Maybe I can disable the camera here, but yeah, you will see it here. So in the chat, I just want to send you, yeah, this is a website where we published a result of a workshop. We had the workshop like 3 years ago. It kind of similar stuff what we are doing now, but I remember back then we had some really problems like finding out the applications of the things which we were doing. But now I can see clearly that, you know, with the recent stuff which we did, with the stuff which I'm talking right now about, that we have some data sets we don't know what to do about. I think that this is really going somewhere, right? Back then we were mostly playing with machine learning. It was like early days, no papers about like modern tools in AI. Yeah, or I mean, there was like a drop off in the number of papers on that for a couple of years, but you can see some examples of what we were doing there, and the students really described it well. So this is, I think it needs to Yeah, you need to click the link to go there. But once it's there, it's there. Yeah, you can take a look. It's quite well described what we did there. So maybe it's another inspiration of what we could do. Tomorrow we will do. So today what we did, the XOR is the regression. Again, we saw how regression, like you saw that we wanted to visualize that one value, right? With the other example is classification. Maybe tomorrow we can have like a small example for regression where it's again evaluating some, like getting some particular value, but then we want to do autoencoders, right? So there's a different story with autoencoders, but yeah, that's what we want to do tomorrow. Okay, I think if there are no questions, we should just end.
Okay. So students, do you have questions? Last chance.
Yeah, last chance today, and then tomorrow we have the entire day for that. And then we have, like, usually you have to tell me, like, we can do the review next week, but we can also do it after New Year's Eve.
Yes, yes. We will decide. Because
it's up to the students. Like, if you see that they want to do something and they just need time, you just tell me. We can do it.
sure. We will, yeah, we will talk about this. Okay, thank you so much for today, and see you tomorrow.
Yeah,
at 10.
See you guys.
Yeah.
Thank you very much. Bye.
10 or 11 is it? I can't remember.
It's 10, but we can make it 11 if it's better for you.
Is it 10? I can't remember right now.
It is.
10. I mean, I have, if it's in the document, it's in the document.
10 till 13, and then from 14 till 17.
If we did it that way, then let's do it that way. Let's not change it. That's fine.
Cool. Okay, cool.
Okay, see you guys.
See you. Thank you so much.